Hello and welcome to lecture 11 of our Essentials of Semiconductor Device Physics course. In this lecture we're going to take a closer look at states of an electron gas. An electron gas is the system of interest to the physics of semiconductor devices, and in this lecture we will also establish a strategy to index the states of an electron gas, and we're going to use this strategy in the next lecture when we derive the very important Fermi-Dirac distribution. Okay, recall that in lecture 7 we considered the system particle in a box. We learned that the states of this system are indexed by three natural numbers, and the energies of these states are given by this expression, where h is Planck's constant, m is the particle's mass, and L is the dimension of the box. Now, in this lecture, we're going to consider the particle to be an electron. And electrons have a spin. So, because electrons have spin, these three natural numbers actually label two different states. One with spin up and the other with spin down. But we're going to ignore this effect in this lecture. So we're going to pretend that the particle, the electron, doesn't have spin, so that each state is still indexed only by the three natural numbers. So we're going to do that because we don't need to take this effect into consideration to understand the physics that lies behind the Fermi-Dirac distribution. We only need that. We only need the effect of the spin in an indirect way, because we need to take into account Pauli exclusion principle, which is a consequence of the spin of the electron. But we're going to still consider that these three natural numbers will index a single state as opposed to two states. So to make it clear what we're going to do, we're going to ignore the spin in the sense that we're going to pretend that each combination of natural numbers denotes only one state as opposed to two states due to the spin. But we're going to take it into consideration in an indirect way because we're going to consider Pauli exclusion principle in our discussion. Okay? So our goal in this lecture is to develop a language and a system to label the states of an ideal electron gas. So the electron gas is just a system particle in a box, electron in a box, but with lots of electrons. That's what the term gas denotes, lots of particles. And the term ideal just denotes that we're ignoring interactions between electrons. So let's recall what we already know. We know that if there is only one electron in the box, then the states are labeled by combinations of natural numbers. For example, 111 is one state. We usually call this a ground state. It's the state with the lowest energy. 112 is another state, 121 is another, 222 is another, and so on. Now if you have two electrons, then each electron will be in a different state, and is the combination of these states that labels the state of the system. So, for example, one electron in the state 111 and another electron in the state 112 labels one state of the system. So, this entire line here labels one possible state of the system, two electrons in a box. This is the state where one electron is in the ground state and the other one is in the state 112. Notice that we cannot, if we have this state, we cannot include in our list the state 112, 111. And that's because the state 111, 112 is the same state as the state 1, 1, 2, 1, 1, 1. If we put both of them, we would be counting the same state twice. And that's because electrons are indistinguishable. This is a feature of indistinguishability of electrons. So we cannot have the state 1, 1, 2, 1, 1, 1 because we already have it. But we could have the state 1, 1, 1, 1, 2, 1. And the state 1, 2, 1, 2, 1, 1, and so on. And if we have 3 electrons, then we need 3 combinations. So notice that the language we've been using is already leading to confusion, because we are using the term state to denote 2 different things. We are using it to denote the state of 1 electron, and we are using it to denote the state of the system. So this is the state of the system, and this is the state of an electron. So to avoid confusion, from now on, we're gonna reserve the term orbital to denote the state of a single electron. And we're gonna reserve the term state to denote the state of the system. So orbital denotes the state of a single electron, like 111, the ground state, or 121, or 211, or 222. And the term state denotes a state of the system, like this is a state of the system, this is another state, this is another state, and so on. And notice that we are taking Pauli exclusion principle into account. And how are we doing that? We are doing that by not repeating the same orbital in a single state of the system. For example, we cannot have a state of the system with the orbital 111 repeated twice, like 111, 111. If we had that, we would be saying that there is a state of the system where the orbital 111 is occupied by 2 electrons, and Pauli exclusion principle forbids that a single orbital be occupied by more than 1 electron. Recall that actually the 3 natural numbers, one combination of 3 natural numbers, actually indexes 2 states, 2 orbitals because of the spin, but we are ignoring this effect. We are pretending that this does not exist because it does not affect the logic we want to learn in this and the next lecture. So we want to simplify as much as possible the explanation. This is why we are ignoring this effect. So in our system, in our pretend system, 111 denotes a single orbital, so it cannot be repeated in a single state of the system. And also recall that we cannot simply swap orbitals, because that would not change the state of the system, because electrons are indistinguishable. So let's take a look at an example now. Let's suppose we want to build a list of states of the system with energy twice the energy of the orbital 112 and 2 electrons. So recall that the energy of each orbital is given by this expression, so it depends on the sum of the squares of the natural numbers indexing the orbital. So the orbital 112 will have energy equal to 1 plus 1 plus 4, so 6, times this term, which is fixed when we have fixed the dimension of the box. So we want states with twice this energy. So we want states with 2 times 6, or 12 times the constant term. And this is the list of states satisfying the condition total energy equal to 2 times the energy of the orbital 112 and 2 particles, 2 electrons. So for example, in this state, the electron in this orbital will have energy 1 plus 1 plus 4, So 6 times the constant term, and the electron in this orbital will also have energy 6 times the constant term, so the total energy is 12. That's the same situation for this state and also for this state. And for this state we have that the electron in the orbital 111 will have energy 3 times the constant term, and the electron in the orbital 122 will have energy 1 plus 4, that's 9. So we have 9 plus 3, that's 12. And that's the same idea for this state and for this state. So here I'm showing how we calculate explicitly the energy of each state. We just sum the energy of each orbital, and we get, in our case, 12 times the constant term, like we've just seen. And since we have 6 states, 1, 2, 3, 4, 5, 6 states of the total system satisfying the condition energy equal 2 times the energy of orbital 112 and 2 particles, that means that the multiplicity of this system evaluated at this energy and at this number of particles is 6. Now let's define a new strategy to index the states of the system. So we're gonna index each state of the system by first creating a huge bracket containing all possible orbitals of the system. So this sequence goes on and on forever, containing all possible combinations of natural numbers. Then we can specify the state of the system by specifying which orbitals are occupied. For example, suppose we want to specify the state of the system 2 electrons in a box, where one electron is in the orbital 111 and the other is in the orbital 112. We can do that by taking our huge list and placing the letter O for occupied on top of the orbital 111 and on top of the orbital 112. And all the other orbitals get the letter U for unoccupied. So instead of using this strategy to specify the state, from now on we're going to use this strategy of labeling the state by placing the letter O for occupied or the letter U for unoccupied on top of the occupied or unoccupied orbitals. So in our previous example of states with energy 2 times the energy of orbital 112 and 2 electrons, we had these 6 states, and now we're going to label them like this. So 112, 121, we receive the letter O here, and U for all the others, 112, 211. So we have the letter O here, 112, 211, and the same for all of them. For example, 111, we receive the letter O here, 122, receive the letter O here, and U for all the others. So we can let go of the previous strategy to label the states and use this new one from now on. So in the next lecture, we're going to ask the question, what is the probability of a given orbital, say this orbital 211 or the orbital 121, to be occupied? And we're going to calculate this probability using this strategy of listing states, and that will lead to the very important Fermi-Dirac distribution. So that's the topic of our next lecture, and I will see you there.